Okay, good morning. So, we have been discussing about the finite volume discretization of scalar transport equation. Okay, and there I explained you that how our different partial differential terms first can be converted into the algebraic terms. Okay, so we saw that we are having one temporal term which is involving the cell or volume averaged quantity phi bar. Then we have convection term which typically can be accounted for by considering the summation of flow of the property at all the boundaries of the control volume. Then we are having one diffusive term. Again, this can be estimated by obtaining the gradient of phi at all the boundaries of the control volume, and then we are having source term. Okay, so what I will do, because the complete discretization of this equation may become little complicated, so what I will do, first I will try to show the discretization of one dimensional convection diffusion equation. So if I simply consider one dimensional convection diffusion term, then it will be becoming easy for us to understand the whole process of uh, discretization. Okay, then you can extend that process for multi-dimensional equation with more number of terms. Okay, so among this equation, which was del rho phi by del t plus divergence of rho v vector phi equal to gradient of gamma gradient phi uh, plus s of phi. Okay, so in this equation, if I have to write this one for one dimensional convection diffusion problem, then how I can write it? First point is, I am only talking about now convection diffusion term, so I will be removing this term and source term. Then I am left with now is one convection and one diffusion terms. Is this point clear? Now, other thing what I can do, because this del operator over here is now del by del x I plus del by del y j cap plus del by del z k cap. So it is pointing in all the three directions. Similarly, velocity vector v vector is equal to ui plus vj plus wk for Cartesian coordinate system. Okay, as I have to only point in the single direction, so I will be taking term del by del x, and corresponding term from the velocity I will simply take u. So one dimensional approximation of first term will be becoming del by del x of rho u into phi. Is this point clear? Now, along with this, in the right hand side, I am having again del, so it will be becoming del by del x. Then I will be having gamma, and then again del phi by del x. So this is now one dimensional convection diffusion equation. Is this point clear? Now, what is the physical meaning of this equation? The physical meaning of this equation is, if I consider a pipe, okay, say at each and every point of the pipe the velocity is same. I am considering the average velocity at the cross section of the pipe. So of course, at average velocity at the cross section of the pipe will be fixed. Now if I consider that at this point I am having the value of phi as phi naught, and at this point value is phi L. So, and whatever medium I am having, in this medium the conductivity of the phi is gamma. Okay, and let us consider, so what is the meaning of conductivity of gamma? This means the rate at which, or diffusion coefficient for phi is actually gamma. So what is the meaning of diffusion coefficient? It means if you make this u is equal to 0, you consider a stagnant fluid between this portion, then how phi will be transporting from one edge to other edge, that will be controlled by a term gamma. Is this point clear? And along with that, if you also add certain velocity, then of course the velocity will also be influencing the rate of transport of phi in the medium. So then it will be becoming a problem of convection and diffusion. All are clear with this point? So physically, when I am considering the convection diffusion problem, I am referring that at each and every location I am only pointing to the average value of the velocity. So if I am pointing to the average value of the velocity, it means that velocity is not changing along the cross section. So variation of all the properties is only taking place along a single direction x. All are clear with this point? Now,
Seven boundary velocity will be zero or boundary velocity, no slip will be there or not?
there can be no slip condition in an actual flow scenario where your interest can be to understand the complete velocity profile, okay, because of the real nature of the fluid. But here we are assuming that whenever we are analyzing this flow problem, we are not considering the variation in the radial direction. Our entire interest is to see the variation in x direction. That's why even if in physical situation there is this type of velocity profile, what I am doing, I am considering its average representative value at that particular cross section. Is this one clear? All are clear with this idea? So what I will be getting now, first what I need to do, so this is my pipe, this particular pipe I need to discretize geometrically. I need to define finite number of control volumes. So let me define control volumes like this. These are the finite sized control volumes. Okay. Now let us consider that in this scenario, the spacing between the two control volumes is delta, the size of the control volume is delta x. If size of the control volume is delta x, then we know that the values will be stored only at which points? Node points, which will be at the centroid of this control volume. If I consider all the control volumes are of uniform size, then I will be getting that the distance between two node points will also be delta x. Is this one clear? And particularly whenever you use the finite volume approach, okay, so control volume you are defining from this point, but this boundary is something which in your physical domain is acting as an inlet because velocity is entering from this point, and this boundary is acting as an outlet. So in order to define the values of the property at inlet and outlet, particularly for boundary cells, we also have to place node point at the center of the face of the control volume. Is this point clear? So this is one additional thing which we typically do in finite volume method, because ultimately whenever I will be defining the control volume, then node point will be becoming somewhere in between. So at the physical boundary of the domain, no centroid of the control volume will be occurring. Okay, so that's why, but values will be available at the edges of the physical domain as boundary conditions. Okay, so ultimately in finite volume approach, what we need to do, we need to define some node point at the face center points in the particular direction along which boundary is lying. Is this one clear? So I am having two more additional nodes at the boundaries, and typically the distance of centroid node to this boundary node will be becoming delta x by 2. All are clear with this point? Now the node in finite volume method which we consider, which we take for our analysis, that particular node which is under observation, that typically I can represent by letter capital P, where capital P is referring to the present node. Okay, then the node which is in east of the present node, that I can represent with E. The node which is on east to east of the present node, that I can represent by E. Likewise, here I will be having W, this is on the west, and this will be on W. Is this one clear? This type of formulation, we are considering only the nodes in this direction because we are trying to solve the one-dimensional equation. if I solve two-dimensional equation, then likewise I will be having volumes in the y direction also. Like for a 2D, it would have been like this. Then I will be having some volumes in this direction also, and then if this is present node, this will be east, this will be west, then one will be in the north and one will be in south of this. Okay, and if you go for a 3D situation, then there will be volumes in the front and in the back as well. Then I will be having one neighboring node in the front side and one in the back side as well. F and B will also come into picture. Is this one clear? So what I need to do now, once I have defined a control volume, after that my next interest is to integrate this equation over the control volume. That is the process. So to integrate this equation over control volume, I will be doing volume integral of del y del x of rho u phi dv equal to volume integral of del y del x of gamma del phi by del x into dv. Is this one clear? Now, if I have to convert this into surface integral, what I will be getting? Summation of all the faces rho u phi dot af. Okay, and this I will be getting summation over af gamma del phi by del x into, and of course this del I can write as d phi by dx because I am only considering the variation in single direction, so it can be an exact differential. Okay, all are clear with this point? Now, because if I consider this present node P, then for this present node P I will be having its two control boundaries. Okay, one boundary is in the east side, which can be represented by small e, and one boundary will be in the west side, which can be represented by small w. All are clear with this point? Now if I calculate this summation term for node P, what I will be getting? How many control boundaries this P is having? Though P is having physically four boundaries, but there is no variation of property in top and bottom. So that's why the variation of property is only taking place in left to right edges. So one is in the east and other one is in the west. So summation of this rho u phi, ultimately in integral form this was rho u phi dot n cap dA, where n cap is considered as the area pointing in outward direction, normal vector to the area pointing in outward direction. So it means I have to consider for east outward direction will be this, for west outward direction will be this. Is this one clear? Now for east, if you consider that your flow is taking place from left to right, then velocity and the area are pointing in the same direction. So that's why rho u phi into AF will be positive at east boundary. Okay, so I will be having rho u phi at east face, and here area is in this direction and velocity is in this direction. So these are opposite to each other. So ultimately I will be having minus sign. So minus of rho u phi into w. This sign can also be understood by another convention. Typically, if you recall, majorly whenever we are writing this entire equation rho u phi dot n cap dA, this quantity represents the net outflux of the property from the control boundary or control surface of the finite size control volume. Okay, so if you have to calculate net outflux, then this quantity is outgoing and from here quantity is incoming. What will be net outflux? Outgoing minus incoming. So from there physically also you can relate it. Is this one clear? Now, rho u phi E minus rho u phi W has to be equal to gamma times again d phi by dx at east face of the present node minus gamma d phi by dx at the west face. All are clear with this point? Now, you will be interesting to note that it is interesting to note that at node P, whenever I have discretized the equation, ultimately all the values rho u phi and gamma d phi by dx, I have to estimate at the faces of the control volume. And if you see over here, where values are known, phi bars are known only at the node points, but at the edges we don't know what is the value of properties as well as the other flow parameters. But whenever we are getting discretized equations, then we need to define all the properties where at the boundaries. Okay, so what we do in this type of scenario, whenever values are available at some other points, but we need to estimate the properties at some point in between the known values, then what we do? Interpolation. Okay, so it means that if we have to estimate all these parameters, we need to use different type of interpolation techniques. Okay, so we need to use interpolation techniques. All are clear with this point? Okay, let us understand how to do interpolation, but before that, let us make certain assumptions. First assumption, let me take that my fluid is incompressible. So if fluid is incompressible, then density will be constant. It will not be changing at different node points, and at all node points and edges, etc., everywhere its value will be same. Let us also make one more assumption, that flow is steady. If flow is steady, then whatever the fluid mass is there at every cross section, that will be same. And along with the steady flow, if I also take one assumption that I am having pipe of constant cross section, like cross section of the pipe is not variable, it means area is same. So I know that mass flow rate in a pipe can be written in terms of rho AU. Okay, if flow rate is constant, if flow is steady, then mass flow rate should not change with time. What is m dot? M dot is nothing but dm by dt. If flow is steady, then dm by dt should be equal to 0. Sorry, dm by dt, yeah, m dot is basically fixed, so dm by dt will be equal to 0. So ultimately, from this you can simply say that if you consider multiple points, say some node P, if you consider rho AU at node P, and if you consider rho AU at node W or any node E, what you will be getting? Density is same, area is same. So ultimately, U will also be remaining same at all the node points. Okay, so if I invoke two conditions, that I am having steady flow as well as the constant area, from this what I will be getting? I will be getting that my UP equal to UW, and that will be equal to U. So it means that in this particular physical system, I can consider that my U, whatever I am supplying at the inlet, same U will be there throughout the pipeline. Okay, so U is again a known parameter to me, and being density as a property of the fluid, whatever fluid I have taken, this will also be a known parameter to me. Okay, similarly, gamma, what is gamma? Gamma is diffusion coefficient. So diffusion coefficient is again a property. So I am considering that this diffusion coefficient under the given circumstances is a constant value. It is not changing with other parameters, and its value is also known to me. All are clear with this point? Now, after these many assumptions, from this equation, which unknown is left? Only phi and d phi by dx. Okay, that is only left. So rho u I can take constant. Inside I will be getting phi at east face minus phi at west face. And this will be equal to, again gamma I can come take outside because that will be constant for all nodes, and d phi by dx at east node minus d phi by dx at west node. All are clear with this point? Now what I need to do? I need to estimate the value of phi e, phi w, d phi by dx and d phi by. So to do so, what I need to do? I need to do interpolation. Okay. Now let us understand. I will be having now different possibilities. This is my node P. This is W. This is E, and this is small e and small w, where I need to estimate the values. Okay. Now how to calculate value at face E? What value you will be defining for phi E? Please tell me.
Average of P and E.
One thing you can consider that you will be taking the linear dependence between E and P to define the value. So you can take, say this is your value of phi P, phi bar P, and this is the value of phi bar E. Then if you take linear relation between these two, then you can define at E as phi bar P plus phi bar E divided by 2. Is this point clear? Likewise, if you consider that your value of phi W is, say, this phi bar W, then you have to define another linear relation in between these 2 points, and you can define it as phi bar P plus phi bar W divided by 2. Okay, so what I am doing, whenever I am doing this interpolation, I am just considering the two neighboring cells, and when I will be considering the two neighboring cells, only which type of relation I can use? Only the linear relation. That is the only possibility. Okay, if I go for third cell also, say if I consider phi bar EE also, then I can fit a curve between 3 points, and based on that curve I can actually calculate the value of phi. Okay, so ultimately there are different criteria. So ultimately at present what I have done phi bar P plus phi bar W by 2, and this entire thing I can simply call as nothing but linear interpolation, because I have only used the two node points, so it can define only equation of a straight line, so it will be a linear interpolation. And if you see with its relation with reference to finite difference method, you will be finding that I am calculating at this point, I am taking contribution from front side as well as from the back side. So it means this has become identical to a central difference scheme. Is this point clear? All of you agree to this point? So now the left hand side I can write rho u into phi bar P plus phi bar E divided by 2 minus of phi bar P plus phi bar W divided by 2. Okay. Now comes the right hand side. Again node P, E, 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 and here at these faces I need to calculate value of d phi by dx. Okay. Now one thing I can consider, that I consider the linear variation property like this. if I take this type of variation, then at this cell boundary, what I will be having? I will be having some discontinuity. Okay, so this discontinuity will be giving me certain errors in my solution. Okay, other thing, if I consider that I am having the constant some average value here and some average value here, some average value here, again in this scenario, if you will try to do calculate the derivative at these edges, this will be again giving the discontinuity. Okay, so here also the variation which will be fitting our data, that will be the one which I have defined in earlier scenario. Okay, in earlier scenario what I defined? That in between this, if I fit a line, then here also gradient will be easily defined and here also gradient will be easily defined. Okay, so if I take this type of linear fitting between point PE and PW, then what will be value of d phi by dx at point E? It will be phi bar E minus phi bar P by delta x. Is this one clear? And likewise, d phi by dx at point W will be phi bar P minus phi bar W divided by delta x. All are clear with this point? So now let's substitute it back. Gamma times, what I will be getting? Okay, so this gamma, this delta x is also again a constant, it can be taken outside. Okay, and 2 also I can take outside easily from the first term. So I will be getting something 2 rho u, and it was gamma by delta x. If I take to other side, it may become delta x by gamma. Okay, is this one clear? 2 times rho u delta x by gamma. And what I am getting inside? Let me not take 2 because 2 I can adjust in the center itself. Okay, so what I will be getting inside, please tell me. From here what I will be getting? Phi e minus phi w by 2. Okay, and on the other side, what I will be getting in the other side, please tell me. Phi e plus phi w minus 2 phi p. Okay, now what is rho u delta x by gamma? Rho u is something which represents the inertial component or advective component, and gamma is something which represents the diffusive component. Okay, so the ratio of rho u by gamma multiplied by delta x becomes a dimensionless quantity, and we can call this as a Pecklet number. Okay, we can call it as a Pecklet number. At the moment, because this is calculated based on the length scale as size of the control volume, that's why I will be calling it as local Pecklet number. Is this one clear? So this is local Pecklet number. This is having certain relevance. That's why I am actually defining it at this point. Okay, so from this what I will be getting, please tell me. Peclet number times, can I further simplify this? Peclet number times phi e, and this phi e if I take to left hand side. So first thing is I will be getting phi bar p. All are clear with this point? First I will be getting phi bar p, and then what else? Minus of phi bar e by 2 and plus phi bar w by 2. Is it correct? Sorry, minus 3 phi bar w by 2. What I am getting? Okay, I cannot take it like this because in the left hand side I am having Peclet number. Sorry. So what you do now, using the Peclet number, you try to take out all the coefficients. Okay. So one coefficient I will be getting 1 minus Peclet number by 2 into phi bar e. Is it correct now? Okay, 1 minus Peclet number by 2 into phi bar e, then plus 1 plus Peclet number by 2 phi bar w, and other quantity I will be getting minus 2 phi bar p equal to 0. All are clear with this point? Is it correct now? Now if you try to make the analogy to AP phi bar p equal to AE phi bar E plus AW phi bar W. What is the analogy? Analogy is that some coefficient with term P is becoming equal to some coefficient with the neighboring nodes. Sum of multiplication of coefficient into value at neighboring node and their sum. Okay. So from here my AP will be becoming equal to 2 and AE will be becoming equal to 1 minus Peclet number by 2 and AW will be becoming equal to what? 1 plus Peclet number by 2. Okay. Like this, I have got the, what I have got finally? An algebraic equation which is a function of the values of unknown parameters at the node points. Okay. Now what I need to do? Of course, this has become an implicit formulation because I need to calculate the value of all phi's which will be initially unknown. Okay. So now, if your problem is very simple, if you have taken multiple node points, here value is phi naught, here value is phi. Ultimately, for each and every node point, you can apply this equation. Okay. However, let me warn you for one thing. One important thing you have to keep in mind, whenever you will be applying this equation for the control volumes close to the boundaries, there you have to take into account the effect of size. Okay. So what will be happening when you will be calculating d phi by dx at this particular edge, then your distance will be this value minus this value divided by 2, because divided by delta x by 2, because this value is known at this point. All are clear with this point? So whenever you will be referring to this boundary node, ultimately when you will calculate rho u phi at w face, then it will simply become rho u into phi naught, because at w face value of phi is phi naught. So in the convection term it will directly become phi naught, and in the diffusion term, when you will be calculating d phi by dx at face w, that will become phi at say node p minus phi naught divided by delta x by 2. All are clear with this point? So this thing you have to keep in mind. Here the treatment of boundary node will be slightly different because of the half distance between the boundary and the cell point. All are clear with this point? Okay, so likewise, can you solve this equation? You can easily solve this equation. Okay, so if you see the solution of this equation, I am just plotting, we are not calculating, I am plotting the general solution. So if you plot variation of phi as function of the length of the pipe, here you consider that at this boundary the value is phi L and somewhere over here value is phi naught. Okay, so here you will be finding the actual theoretical solution. Actual theoretical solution will be something like this. Is this point clear? Because why it will be like this? You can see the value of phi naught at left boundary is greater than phi L. So from left side, what will be happening? Because flow is happening from left to right, then phi naught will be propagating towards the left side. So this will be physically the solution when u is greater than 0. If u is less than 0, then which value will propagate? So phi L will be propagating and it will be something like this. This is for u less than 0. And when u will be equal to 0, then what will happen? Pure diffusion, that should be a straight line. So this is for u equal to 0. All are clear with this point? If I have to write this in terms of local Peclet number, then also this u I can simply, because all the other parameters in Peclet number are constants. So this will be for Peclet number greater than 0, this will be for Peclet number equal to 0, and this will be for Peclet number less than 0. Up to this point, is it clear? Now, your numerical solution, whatever the equation we have calculated, there we assumed that u is greater than 0 because flow is from left to right, it is towards the positive x direction. Okay. So in this scenario, what should happen? When I will be plotting this is my theoretical solution. So my numerical points should comes closer to this. Of course, these may be slightly up and down, but of course the final solution should be at boundary nodes. Of course, this will be exactly coinciding because we are not calculating the values are already known to us, but in between my solution should be something like this. Okay, so right now which scheme I have used for convection term? Central difference or linear interpolation. Okay, as well as for diffusion also we have used the linear interpolation. Okay, so you will be finding that your this type of solution will be appearing when the value of local Peclet number, the Peclet number which is calculated by considering delta x as the length scale, when value of local Peclet number is less than 2. When value of local Peclet number is less than 2, you will be getting this type of solution. But if value of, so all of this, please, this is something which now you can physically verify. So all of you have to now practice small code. This equation is very easy to code. Okay, so what you can do, maybe if required, then I will share one of the code with you. Here you can test all these things. Okay, so whatever the observations I am just representing here from my say experience, all these or from the textbook knowledge, all these experiences you can actually try by your own, and by just doing the variation of delta x in your numerical code, you will be seeing that one time solution is coming like this, other time it is coming some other way. Okay, so all these things you can actually try with the help of a code. So this was the theoretical solution. Here, if I take a scenario where Peclet number is greater than 2, you will be finding, of course, boundary nodes are same. You may find some solution, something like this. This is nothing but a which type of solution? Oscillating solution. Okay. So it is not following the particular trend, and even so this will be for Peclet number greater than 2. As you will be moving far away from the Peclet number 2 condition, these oscillations will be becoming more rigorous and you will not be able to make any conclusion out of the results whatever you are calculating. Okay. So can you tell me what could be the possible reason for these oscillations in my solution when Peclet number is becoming greater than 2? Delta x is large. So what is happening because of?
Cannot capture between the plane.
Okay. So one important thing comes from here. Let me tell you. Whenever you estimated the value of, this was node P, this was east face, this was west face. When you calculate the value of phi e at east face, what you did? You have taken the contribution from P node and from the which node? E node. Okay. And what is this phi e? This contribution is purely because of the convection term, because this was associated with the flow rho u phi e. So if this value is affected by, convection term, then what should happen? Please tell me, what should happen? This value should be dependent upon the value of phi coming from the upstream direction. It should not be dependent upon the value in the downstream. A simple example is, in your Reynolds experiment, what you do? You have water and you put some ink, okay, and that ink then propagate in the downstream direction. If you have to determine the concentration of ink at this point, which is in which direction? Upstream of the needle. And for calculating concentration, if you consider node point from downward direction also, what will happen? Some amount of ink will be visible here also. But in real practice, if I am talking about pure convection effect, then at this point there should not be any effect of ink. So what should happen? And ultimately, other way you can also understand like this. Say ink is coming like this. If at any point ink has reached up to this point, and in the next point you want to measure after time delta t, what will happen? So what will happen? If flow is from left to right, then this ink will be reaching this side. Okay. So it means the flow will be, the value will be influenced by the upstream direction. But if you consider at this point that after delta t it will be average of this and this, then what will happen? Your solution will be wrong, because whatever the value of ink was supposed to be at this point in concentration, if you take this variation, then this 0 while taken in average, it will be diluting the concentration. All are clear with this point? So ultimately, there has to be some property of the numerical scheme which should be satisfied for the convection term. That particular property is called as transportiveness. Okay. So a numerical scheme should be transportive in order to have the proper solution. And this transportiveness property is only required from the numerical scheme when flow is involved, convection is involved, because convection will be giving some specific directional preference for variation of the variables. Okay. So whenever I estimated this phi e, I have considered phi bar p plus phi bar e divided by 2. Okay. So here for convective term I am using the averaging from both the directions, which does not satisfy the property of transportiveness. Based on the property of transportiveness, the value of phi, because of convection at node E, has to be dependent upon only the previous node point. Is this point clear? So because I am using linear interpolation for convection term also, that's why my transportive property is not being satisfied. Then the question can come, if transportive property is not being satisfied, then why solution is coming good for Peclet number less than 2? Now can you answer this? Can you answer this point? See, what is Peclet number? It is rho u delta x by gamma. What does gamma represents? Diffusion, and rho u delta x represents convection. When Peclet number is less than 2, then the order of convection and diffusion is nearly same. So in this scenario, what will be happening? The rate at which from P to E information is propagating, that will be slightly deviating from the proper circular shape, but this deviation will not be much because convection and diffusion are almost of the same order. Okay. On contrary, so it means, sorry, so when convection and diffusion are of same order, the moment in which the diffusion will form circle, in the similar movement, convection will also be propagating almost with the same pace. Okay. So when both are approaching with the same pace, then consideration of dependence on both the parameters will be giving the correct formulation. But if my situation of Peclet number is very large, okay, in that scenario convection will be dominating, so purely information will be propagating something like this. The effect of diffusion will be actually vanishing. So in this scenario, what will happen, that when Peclet number is approaching to 0, okay, which is a situation of almost pure diffusion, there the linear interpolation will be working fine. When Peclet number is approaching to infinity, their linear interpolation will not work, because ultimately that problem is becoming convection dominant, and for convection dominant the preference to direction has to be given. Okay. So in this scenario, what is done, because for you will not be able to every time consider your delta x in such a way so that you can maintain your Peclet number less than 2, then ultimately you have to take large number of cell and your computational cost will increase. So we have to find some alternate way with the help of which we can avoid this issue. Okay. So what typically we can do, we can take certain schemes where for estimating the value at every phase, because of the convection effect, I will be giving preference to the upwind direction only, and this type of schemes are called as upwind differencing schemes. Okay. So in case of upwind scheme, what will be happening, say if value of phi is phi bar p in this and value of phi is phi bar e in this, so ultimately when I will be calculating the value of phi at east node for u greater than 0, I will be considering the I equal to phi bar at p. All are clear with this point? So at this phase I am calculating, flow is happening from this side. So what is upstream node? Upstream node is P. So whatever the value is there at P, same value I am assigning to. All are clear with this point? Okay. Though the order of accuracy of this will be less. Central difference, linear interpolation was first, second order accurate. Now this will be first order accurate. However, for estimation of d phi by dx, I will be using the same property. Okay, I will be using the same term. So, this is one difference where upwind differencing schemes are preferred. Upwind differencing schemes, though, gives the. Do you have class after this? No? Yes? So you can leave. So say this was the theoretical solution. When you will be using upwind differencing scheme, your solution will be close to theoretical, but if your flow velocity become very large, then this solution will be deviating significantly from the theoretical. So there will be some numerical diffusion. This is called as artificial diffusion or numerical diffusion. Okay, to avoid this numerical diffusion, what is done, instead of using the only one upstream node to define the value of phi, multiple upstream nodes are also used. So these are called as higher order upwind schemes. Particularly one of the higher order upwind scheme, you might have heard the name, is quick, QUICK, quadratic upwind interpolation of convection term. Okay, so of course, because this course is not specifically meant for computational fluid dynamics, here we have to do CFD of multiphase flow. So those who are interested, they can refer to the recordings of computational fluid dynamics. There I have explained the quick, and there are certain situations where quick also fails, then we have to go for the total variation diminishing scheme. So all these things you can get in the CFD books, as well as you can refer the CFD recordings. But what I want to establish over here, I want to just, my motive was to give you the basic idea, so that now whenever we will be extending our discussion on CFD of multiphase flow, we should be able to then apply all these operations on the multiphase equations. Okay, so one important point I would like to establish over here, one of the behavior I have explained for a numerical scheme, that was transportiveness. Similarly, a numerical scheme should satisfy three important criteria. If any numerical scheme is not satisfying these three criteria, then whatever the outcome we will be getting, that will be absurd and it will be of no value. Okay, so first is conservativeness. Second is boundedness, and third is transportiveness. So the meaning of conservativeness is, so typically whenever we will be using the interpolation functions, we have to choose in such a way so that all these three behaviors are satisfied. Okay, for example, one example I have given you there. Okay, let me plot it over here only. In one of the case, I told you, if this is my point P, this is E, this is W, then I could have taken interpolation function something like this. But if I take this type of interpolation function, then d phi by dx for the left, this particular east face of P will be different, and for west face of east will be different. So if this type of difference is there in the outgoing flux from the cell P and incoming flux to the cell E, then my scheme will not be conservative. All are clear with this point? So ultimately we have to choose interpolation function in this way so that whatever is the flux leaving from this edge, same should be the value of flux entering the other point. Otherwise, because of the flux discontinuity, there will be some error. So the scheme which does not satisfy this type of behavior, that is actually not conservative. So in order to have flux continuity, scheme should be conservative. Transportive behavior I have already defined. Transportive behavior means whenever you are estimating the convective terms, then your scheme should give preference to the particular direction from where the information is propagating towards that particular nodal value or say edge value. Third property is boundedness. Boundedness is a very simple property that if your uh, this is phi naught, this is phi L, and this is the theoretical solution, then solution should be in between the value of phi naught and phi L unless or until any source term is used. Okay, it should not oscillate and go beyond the bounds of the phi naught and phi L. So that type of property is called as boundedness. So any numerical scheme, it will be only giving you the useful results once it satisfies the properties of conservativeness, boundedness and transportiveness. Now we will not spend much time on this CFD issues. In the next lecture, I will briefly discuss one of the method for discretization of Navier-Stokes equations, and after that we will be moving our discussion for computations of multiphase flow. Okay.